Okay, so we are still waiting for some students. Taking this time, if you have any questions regarding the first assignment, please feel free to ask.
Yeah, I have a question. We submit the JSON file, right? It's enough, right?
No, you submit a CSV file.
CSV?
Yeah.
Oh.
Yeah, because CSV file is basically one line per annotation, right? So we can easily concatenate and share with the students later.
Oh, that means we can directly extract the CSV file from the BIA, okay?
Yeah,
then
yeah. So
submit
basically, when you're annotating, you save as workspace. Okay, you keep that workspace actually. Okay.
Mm-hmm.
And finally, when you are done, you export a CSV annotation file and upload.
Okay.
Thank you.
Thank you. Thank you so much.
Then
another question I have. When I return back to check what I did from CSV,
yeah,
how to check that again?
Oh, so there's a you can basically use another workspace, right? Basically, you can refresh the browser using an empty workspace, and then you load all the 10 images, okay? And then you import the CSV and see whether it works properly, okay?
Okay.
Yeah, if it doesn't work properly, some of the annotation are not shown. Basically, it's because you didn't click the label, okay? You didn't click the label somewhere. Like, for example, after draw a polygon, maybe you didn't click the class. And in that case, there will be an error there, and all the rest of the polygons will not be shown. And you need to pinpoint what's the largest ID there, and open the annotation file using the text editor and find the place and replace it with the right label. Okay.
Okay. Thank you.
You're welcome.
One thing I noticed is we had one document with one set of labels on it, and then another with another set of labels. And they were like very similar, but one said like bolt head and one said just head. I know you probably want to keep all the classes exactly the same. So which was the correct set of classes?
Oh yeah, so let me, this is important. Yeah, let me reiterate the requirement. Let me stop this. Yeah, so in the documents that I shared, there are two documents. One is the instruction. In the instructions, there are some annotations, but don't take these annotations like screw head as the annotation. Okay, this is just a walkthrough of VS software. The actual instructions are here. Okay, the actual instructions are here. So you need to go through this instruction telling you what we are expecting. Basically, it's head, thread, nut, pin, and washer. And HT, these kind of things should be uppercase, right? So because we will merge all your annotations, right? So if someone use lowercase h, some use uppercase h, they will be treated as different classes, okay? So basically something like this will be perfect, okay? So add, thread, nut, pin, and washer on page 10 of the instruction. Did I answer your question?
Yes, and you said not to capitalize, correct?
Yeah, capitalize every class.
Okay, capitalize all of them.
Yeah, just follow what is in the assignment instruction. Okay.
Perfect. That answers my question. Thank you.
You're welcome. Yeah, if you didn't, let's say you didn't name it like this, you can open the annotation file, replace all. Let's say you have a lowercase hat, okay, and then you want to replace it with the uppercase hat. You can go to the annotation file and replace all. Just a walkthrough of the annotation file. I think there's an annotation file here as an example. Again, you need to open with, let me see. Find any text annotation file, okay, and open it, right? So, and then let's say you accidentally name it as lowercase, right? So you just replace all with lowercase using uppercase, okay? That will solve the problem. And keep in mind, again, if you see anything that is ID, let's say 10 in the image, right? So in this image. Okay, you come to the annotation file, you should look for 9. Okay, because here it starts from 0, but in the annotation interface panel, it starts from 1. Okay, there's a 1 difference. Okay, and sometimes if you forget to click this, this will be undefined. Okay, you have to put it back, and you need to follow exactly the shape. Right? So quotation, quotation, no, the class name, quotation, quotation. Okay, otherwise, if it finds something undefined, the rest will be ignored. You will not see anything here. Okay. Yeah, any other questions? If not, we will begin.
Just one question.
Hello? Yeah.
Yeah, this is Pat.
Yeah.
One of my file has like, hundreds of nut bolt annotations.
I see.
More than 100. Yeah.
So you expect there should be not more than 100. Okay, so if there's more than 100, then if truly the image you are unlucky get assigned more than 100, you find those top 100 that are more up to the front. Let's say these are up to the front. Okay, these are not important. It's okay.
Okay.
Not important. Yeah. So so use your informed guess to know like these things are important. Right. So if you fly drone here, you probably are not care about these. Right. If you care about these, you will fly your drone lower, right, to these places. Is it okay?
Yeah. Okay.
Yeah. If you find that you have more than 100 objects to annotate, just send me an email. Okay, I will take a look.
Okay.
What about the one that you said that are not important? What if you ended up annotating them? Do you lose point for those? Because I also have.
If you annotate more, you definitely will not lose point. Actually, we will give some bonus points. There's a formula to calculate. If you annotate all of these, that's fine. Okay.
Because I have. I think one of my files had more than 100.
I see. If you want to play safe, definitely it's fine. But if you think it's a little bit overwhelming, you can send me an email. I will tell you which one I think is the most important. Okay. Yeah.
Okay.
But try to use your informed guess. If it's not too many, try to annotate. Let's say for all things on this line, obviously it's important. Right? So because this is where the drone is trying to check. Okay. But there's something down there, these things may not be that important. Okay. And also something in the back. Right? So there's also something in the back that doesn't matter. Okay. All right. Any other questions? If not, we will continue. And I know that some students get the files later. So for how many days you are late, you are allowed the extension for how many days. But you need to request that explicitly with the TA, okay? And so that he can keep a note, right? So you can directly reply with the email that you request for the files again, for example, right? So that the TA has a date. Then we can keep a book, and because there will be so basically if you submit late for each day, we will have 5-point deduction. Okay, so if you submit late for more than 1 week, we probably will not accept the late submission. Right? So try to be on time, and if you get extension, we will not deduct point until the new deadline. Right? Okay, let's continue. So today we will talk about, let me put this blocking to a good position, okay? So we will talk about Bayesian decision theory, okay? So this is very important, especially in graphic models. Everything is Bayesian or conditional probability, okay? Let's take a look at it. So firstly, the introduction, okay? Let's consider a toy example called a coin tossing example, right? So basically, you have one coin, okay, and you toss the coin, right? And when it becomes stable, either the head is up or the tail is up, upwards, facing upward, okay? And we can use a random variable, x to, actually it's a binary random variable. It can only take 2 values, right, to denote the result, okay? 1 means the outcome is head, and 0 means the outcome is tail. And how can we model this this outcome, right? So it's random variable, okay? Random variable is a variable which can take a 0 or 1, a head or tail. But it's random, right? So sometimes it's hat, sometimes it's tail. Okay. So because of this reason, you can define a probability distribution over the value, by the value field. Okay. Because this is a discrete distribution with only two values, right? You have a probability mass function. Okay. If you have a continuous distribution, you have a probability density function, right? I assume everyone knows what is PDF and PMF, right? So let me know if you don't. I will go through that. Okay.
Professor, can you go through that as well?
Okay then, yeah. So PMF is a probability mass function. Okay. PDF is probability density function. Probability mass function is something like this, right? So you can have a random variable takes three values, 1, 3, 7, but their probability is 20%, 50%, and 30%. Okay. The probability is sum of 2, 1. Okay. And there are three options. This is called the probability mass function, okay, PMF, right? And so it's for discrete random variable. Okay, if you have a continuous random variable, then we have a so-called PDF, because then you have density, right? Because if you look at here, the density is infinity, right? So for discrete distribution, we don't have density. Let's say if you think about it, this is 50%, right? So this is 50%. But you want to compute the density, right? So you have the width here, but the width is 0, right? Divided by 0, this is infinity, okay? So for discrete random variable, okay, we only have the PMF, okay? Now, if you have a continuous random variable, right? So let me see here. Let's directly go to PDF. Yeah, if you have a continuous variable, right, so then you can take values from a continuous range, right? So let's say the temperature of yours. Right? So if you do a test on your temperature, it can be anywhere from here to here, right? The human, maybe this is the normal temperature range, right? So in that case, this is the continuous distribution, right? So then we have a density, right? This is less likely, this is more likely, this is unlikely, right? So it's low temperature, or you have some trouble, okay? And in that case, there's a density distribution, right? So if this width is 0, right? So you say, hey, I'm at my temperature from A to B, right? Which is a small range. Then the probability is this bar area. Okay, so the whole area is 1, right? So this is density distribution. And in density distribution, if you look at just one point, the actual density is always 0, right? Because you take integral over 0, right? But there's a density, okay? As long as you take a finite dense, which is not 0, you will have it. Pranesh, did I answer your question?
Yes, Professor. Thank you.
Yeah. And there's also a concept called a PDF, right? So PDF is a CDF. Okay, so cumulative distribution function, right? So this is basically take an integral. Okay, so take an integral of this PDF, give you the CDF. Okay, continuous random variable. Then fx is the PDF, right? So f is the PDF. Okay, or the probability mass function, and then you take integral from negative infinity to current size, right? So then it's a CDF. Okay. So for example, if you look at this, let me see where is the example here. So anyway, so this is saying that the probability that your value is all the way up to B. What's the total probability, right? So if you look at the PDF before. Right, so if you want to get a CDF here, right, so it's the area here is the CDF value, okay? Right, if you get a CDF here, the area here, okay? So these are concepts we assume you already know. If you don't know, I think we have gone through, okay? An example is, let's say, Gaussian distribution. Or we say normal distribution. So the PDF and CDF are something like this, okay? So the PDF is say, hey, this is most probable, right? So it's a Gaussian distribution. The mean value is the most probable. And there's a farther away from the mean, like 2 standard deviation, this is less likely, okay? Now the CDF for this curve is something like this, right? So because, it's computing something like the area here, okay? Right, so in the middle, it's 50% because, this is half of the area, okay? And you can see that it's a plateau here in the beginning because, this area is not increasing initially, it's a plateau, it's almost there, okay? And here you can see here, if you go to here, this is again plateau because almost all the area here, right? The rest of the area is almost there, okay? So that's why it is. Right, so this is CDF, this is PDF. Is this okay?
Thank you, Professor Anderson.
Okay, yeah, so just in case the terminology, I believe if you learn calculus, right, so you should, probability theory, right, so you should know this, but maybe the terminology, right, if you are from abroad, so maybe this is a good recap. Okay, so yeah, so here we are having, PMF, right, mass function, okay, because it's a discrete, only 2 values, sorry. Oh, that's why. So we cannot use, somehow, at least for me, the Zoom's pen is not working. Okay, we want to play in this one. So here you can see that we can only take 2 values. So it's not PDF, it's a PMF, okay? So the PMF, we use uppercase P, okay? If it's PDF, we use lowercase p. This is the habit, okay? So this is the PMF, this is PDF, okay? So X is Bernoulli distribution. Bernoulli is just like this, right? With the probability P, you succeed, okay? P0, you succeed. The probability 1 minus P0, you fail because they have to sum up to 1, okay? So now, actually, Bernoulli distribution can be represented using this formula, okay? Why? This is actually very simple, right? So think about this formula, and if you think about the first case, X equal to 1, what will be the probability? Who can answer me?
P0. Half. 1 by 2.
P naught.
Yeah, P0, right? So it's P0,
Yeah.
okay? Yeah, it's may not be 1 by 2, okay? This is the probability that the outcome have, right? So it may not be 50%, okay? So you can see that if it is 1, then this is P0 to the power 1, but this is something 1 minus 1 is 0, okay? So this thing to the power 0 is 1 always, okay? So this term basically times 1 is gone, right? So you only have P0. Is this okay? Yeah, assume it's okay, right? So if you have a question, let me know, okay? Now the second case is, 0, right? So if it's 0, what will happen? What's the result? Who can answer me?
P naught. 1 minus P naught.
Yeah, 1 minus P naught, okay? So the reason is also very simple, right? So if this is 0, then this to the power 0 is 1. This 1 times anything is still the same. So we just look at here. And because this is 0, right, so this term is 1. To the power 1 is just this. Okay? So this is basically a succinct way of describing this, right? So basically it's saying that if X is 1, then probability 0, okay? Outcomes have. If X is 0, then you get the other probability, right? So 1 minus P. Okay, let's say if you 20% of probability you have had, right? Then 80% probability you have. Okay, so this is a Bernoulli distribution. So so this is called Bernoulli test, right? So you have certain probability you succeed and the other probability you fail. Okay, so again, so if you look at the Wikipedia, it's the same thing. Okay, so these are the variants, goodness, but I believe we have the PDF. So yeah, PMF. Okay, this is a discrete way of describing this, but we can make it more compact like this. Okay, because of the reason. Right? So basically, if you get 0, it gives you 1 minus P. Okay, if you get 1, it gives you P. Okay, usually we will use this one because this is something we can take a derivative, okay, which is very important when we do something like gradient descent or compute the optimal value. Okay, we don't want to use this. It's not so uniform. Yeah, so basically there are 2 forms, right? We are using this form. Okay. Any questions?
Professor, could you give some intuition as to the difference between Bernoulli distribution and Gaussian distribution, or sorry, not Gaussian, but regular normal distribution? I know normal distribution is probably density function, but Bernoulli, how does
Okay,
it?
so Bernoulli distribution, you can only take 0 to 1, okay?
Right.
Gaussian distribution, you can take all the values here, okay? I don't see any relation between them.
Okay, right. Just
This is PDF Gaussian distribution, okay? This here the Bernoulli distribution is PMF because it's a discrete variable. It's okay?
yes, I understand. So one's PDF, one PDF PMF, right? Gotcha.
One only can take the binary values, right? 2 values. Another can take an infinite number.
Bernoulli is discrete distribution, right?
Yeah, here this Bernoulli is just discrete, only 2 values.
Yeah.
And yeah.
Professor, Bernoulli distribution is related to binomial distribution, right?
Oh yeah. So binomial distribution is a bunch of independent Bernoulli tests. Okay, right. Each time you have the coin equal to head, right? So then if you flip 10 times, how many head you get, right? So each time, so binomial distribution is a sequence of the Bernoulli test. It's okay.
Yes, sir. Yes, sir.
And you get the count. Okay, so yeah, they are related. When you learn probability theory, this must be there. Okay, so but yeah, it's a recap. Oh, unfortunately, let me see. Yeah, I used this again. Okay, so now what we want to do is this, right? So we want to estimate what's the probability P0, which means what's the probability that you will get head instead of tail, right? So the probability can be estimated like this, right? So this is pretty obvious. Let's say if you toss 10 times, you have 4 times the head, right? So you think it's 40%, right? So we will make it more strict later, okay? But this is basically how you estimate P0, right? So this is what we say, right? If you have a model F and you have a theta, right? Here theta is P0, right? Okay, and then you see the data X. Okay, so X is you flip 10 times and 4 of them are heads, right? And then you estimate this parameter, right, to be 40%. Okay, so this is what we are doing here. Right, so Y equal to this. Right, next time if you have another flip the coin, right? Next time you have another coin flip, then you want to predict Y. Okay, in this case, 40%, what will you predict? Anyone can answer me? It will be tail, okay? Because only 40% is head, right? So tail is the safer choice. You will always predict tail, okay? If you have a question, just stop and ask. Yeah. And yeah, so basically we can write it like this, right? So N is how many times you toss a coin, right? So this is training data, right? So the training data is something like this, right? 0, 1, 0, 1. 1 is a head, 0 is a coin, tail, okay? And N is how many times you have. Let's say we have 10 times, okay? This is sum of all the values, right? So this is actually a trick, right? So we still can sum all the values because this is basically count how many ones you have. Because if it's a tail, it's 0, then the summation, it's not added to the summation, right? Only when it's head, it's added to the summation. So this is the number of heads, okay? In general, if we have more classes, we will define indicator variable, right? So if it's a York paired class, that's a head, it's 1. Otherwise, it's 0. Then you can use this kind of summation to count how many is the kind of thing you care about. Okay, we'll see that later. Right, so then we can, this is training, fit, okay, fit 40%, okay? Now we predict, okay? So predict the outcome should be either head or tail. But what we will do is if our head probability is larger than 50%, we assume it's head, right? Otherwise, we will always predict tail, okay? So because last time we see it's 40%, we will always predict tail, okay? Any questions? Okay, so basically by choosing the more probable outcome, right, minimize the probability error, right? So for example, if your error, your probability of head is 40%, right? Then you choose tail, okay? Tail, the probability is 60%. So your correctness probability, accuracy is 60%, okay? Your probability of making mistake is 1 minus 60%, which is 40%, okay? So the probability error is minimized. Because if you had the probability error is 60%, right? If it's tail, the probability error is 40%, okay? So of course we prefer the small error, so which is tail. Okay, then let's look at the Bayesian decision rule. Okay, so let's go back to the credit scoring example. Okay, credit scoring example. So again, so I think this may be a new example. Previously, engine and power and family car. Right? So it's the same thing. Okay, so basically, if you have income, you have saving, right? So then people can say, hey, whether I should approve the credit card for you or not, right? So and of course, if you are categorized as low risk, which is 0, then yeah, so I can approve the credit card application. If it's 1, then I cannot approve the credit card, right? So you need to get more credits. Okay. So in that case, this is why. Okay, it's a classification problem. Okay, and you also have X. X is the 2 features. One is income, one is savings. Right? So, for example, for income, even though you don't have much savings, right? You don't have much money, but each year, let's say you make $1 million, right? Or each month you make $1 million, right? So why not approve it? Okay, it's safe. You will return the money. Okay. On the other hand, if you have no job, let's say your dad is super rich, right? Billionaire, right? Okay, you have a lot of saving account, right? I can steal your money, right? So there's a trade-off, right? So how much you already have, how much you are making incrementally, right? So these are the 2 features, okay? And here's the prediction, okay? So let's say given these 2 attributes, right? So if we finally decide, hey, you're safe, right? You're high, oh, this is, let me see. If you are high risk, right? So I should not approve, right? So then I predict high risk. Okay. Otherwise, I predict low risk. Right. So, but this again now becomes a X, Y. Right. So X is the input feature, Y is the probability. Okay. So here we have 2 parts. The first is kind of like a regression problem, but it's special, right? We build on probability theory. Okay. You have a feature vector X. Okay. Based on that, you will predict the probability, which is Y. Okay. But then based on this probability, you will make a decision, which is the actual final one. Okay. Basically, if let's say we decide your risk is more than 50%, right? So what we will do is, hey, I will rank you as high risk. Okay. And otherwise, if your high risk probability is less than 50%, I think you are not risky. Okay. Any questions? Okay, let's continue. So this is the equivalent form. Okay, so equivalent form is basically saying that, hey, so basically we are saying that these 2 conditions are equivalent. Okay, it's very easy to see, right? If this is more than 50%, let's say 60%, then this is 1 minus that, which is less than 50%. Okay, so this is always larger than this. Okay, they are equivalent. It's not difficult to see in the binary case. Okay, if 1 is more than 50%, the other is less than 50%. This is definitely more than that. Okay. And if you are more than that, if you divide by 2, you know that 1 is definitely more than half, right? This is less than half. Okay, so this is 50%. Okay. And if you have a difficulty access UAV box, CC Jalal, okay, or write to Jalal and CC me. Okay, he will handle it. And you need to do that as soon as possible because we have released this early on. Right? So I see that students, some students didn't read the requirement carefully. Okay, so if you look at assignment, yeah, so I try to keep things simple. Let's say for assignment, I don't want a long document. That's so only 4 or 5 sentences. This is my style, but you do need to read these sentences carefully. Right? So for example, you will receive an email on this date containing 10 images from UAV box. If not, please contact Jalal or me. Right? So this is you need to do right on that day when we release. Okay. Right. So if you didn't do that, then you need to do that as soon as possible. Okay. Yeah. Okay, let's continue. And what's the probability error, right? So the error is basically this. Okay, why? Because for example, if you so this is the probability that so basically what you will do prediction is you choose the most probable class, right? So for example, this is more probable, then you would choose this one, right? 60%, okay? Then the probability that you make error is 40%, right? So which is 1 minus that. 1 minus the bigger one. Bigger one is what you will take, right? So the bigger one is what you will take, okay? According to this, right? So this is why we have max. If this is bigger, then we will take 0, right? So we always take the bigger. Any questions? So we will see this kind of rule happening in this this lecture and maybe the other lecture for binary classification. Okay, binary classification is a little bit special. Okay, so again, so you don't have to always take a 50% as a bar, right? So for example, you want to really play safe, right? If according to this, even though you have only 10% risk, okay, of being high risk, right? I will still reject you. I hope anyone, if after getting X, the probability is less than 5%, right? I think it's safe, okay? So in that case, so this threshold you can tune by yourself, okay? So this actually goes to another story, right? So, so you can adjust this for binary classification only, okay? So this gives you some concept called AUC, ROC curve, okay? So something like this, right? So we remember last time we talked about false positive, false negative, true positive, true negative, right? So now if you have different criteria, right? So let's say originally think more than 50% is true, okay? Now I think more than 10% is true, right? Okay, it's true, okay? Or more than anyone below is false, okay? Right, so the criteria changes, right? So then your predicted amount of true and false will change, right? The ground truth doesn't change, but the true positive, false positive, true negative, false negative will change, okay? Right, so this changes because your threshold of binary classification changes, okay? And if you change this threshold from 0 to 1, you will have different false positive and true positive rate, okay? And this will allow you to pull out a curve, okay? And this curve basically, it's called ROC curve, okay? And the area below it is called the AUC, okay? Area and the curve, okay? AUC. So the larger the AUC, the better the area, right? The largest area is of course 1, because the edge, both edges are 1 times 1 is a square, okay? And the better if your curve is more to this corner, the better, okay? The reason is very simple, right? So this is a true positive rate, right? So of course, if you are correct and it's also true, right? Both aligns as the larger the better, right? This is for the positive rate, right? So of course you prefer, if it's fake, you don't want to rank it positive, right? You want the rate to be as 0 as possible, right? So this pushes you basically to this corner, okay? 0, 1 corner. So if your curve finally is something like this for your model, it's gonna be better than this model. This only applies for binary classification, where you can change this threshold, okay? So this is a side note that we didn't cover earlier, right? So, and in general, there are a bunch of scores that you might want to know. They're all defined on the true positive, false positive, true negative, false negative, okay? So here there's oh, by the way, why we care about this, right? So this is a better metric because you have class imbalance problem, right? So let's say your positive class has 2 items, negative has 8, then simple accuracy may not make sense, right? So for example, if you always make it things positive, right? Because majority positive, your accuracy is very high, okay? You just assume everything positive. Let's say you detect COVID-19 patients, right? So maybe in 100 people, only 1 or 10 is COVID-19 patients, right? So if you always predict negative, right, you get a 90% accuracy, but it's useless, right? So you never detect any COVID-19 patient, okay? So in that case, you want to use ROC curve to compare the model, see what you want to do, right? You just change all the structure, okay? And so there are a lot of definitions, okay, and based on here, so these are the common ones, okay? So based on these 4 numbers, you can define recall, right? Sensitivity, they are the same thing, okay? Specificity or selectivity, yeah, another thing, right? So precision and accuracy are different. Right? Precision is saying, hey, among all the things that I rank positive, how many are actually positive? Right? So let's say I assume these people have COVID-19 patients, right? So maybe 100 of them, actually only 80 of them, 20 of them are not, right? So this is precision. Accuracy is different, right? So accuracy also cares about whether the negative one is predicted as negative, positive one is predicted positive. Right? So that's different. So they have all kinds of metrics which you can report for binary classification only, okay? Keep in mind this thing is only for binary classification because you only have true or false, okay? And again, so the AUC curve, let me see, I use this ROC curve and the AUC, okay? Yeah. So this is area and the curve. Okay, so this is what we just talked about. Basically, it's the area and this curve. Okay, the larger the better. It's more towards this point. Okay, so this is when you have a binary classification problem with sexual thresholding, right? So then you can use these metrics. Okay, this will allow your paper to evaluate from all kinds of metrics. They all have different preference, by the way. You can read their explanation. Okay. And the precision and recall together, there's another score called F1 metric. Okay, and if you are doing like a web search, web mining, you care about both precision and recall, then people will report F1 metric. Okay, right. So they have different preferences. Like precision means if you rank those 100 people as positive, and how many are actually positive. Recall is actually there are so many positive, let's say COVID-19 patients, right? 1,000. How many you actually find out? So maybe only 10, it's not good. But all of them are actually true positive. So the precision 100%, recall is maybe 1%, okay? So you care about both and you have something like F1 score and a lot of metric value. Again, keep in mind, this is only for binary classification, okay? And if you want to change the threshold, you will get ROC curve. And then you will have the AUC area and the curve to measure, okay? And you also have the confusion matrix, which is not just for 2 class. Okay, so let's go a little bit more. So for cat dog, you have the confusion positive. This is the confusion matrix for 2 class, but you can have more. Okay, so for example, let's search for let's go a little bit beyond the test box. Okay, so this will help. Okay, so for example, this is a 3 class classification. Right, so there are 3 classes, 1, 2, 3. Okay, and of course the best is on the diagonal. Right? So if your setosa, the true label and your predicted label match, right? These are the best. And you want to minimize those. Okay, maybe some may not be 0, then it's not so good. But this is called confusion matrix. Okay, but only when your confusion matrix 2 by 2, then you have those metrics you define it. Okay. So binary classification is a little bit special. Okay, so again, if you have interest, you can delve a little deeper. Okay, so these are basically the metrics that you can use, especially for binary classification, to report in your report or experiments to compare different models. Okay. All right. So and finally, so these things are there. You don't need to compute them. Okay. If you look at scalar matrix, okay, everything is there. So yeah, these days coding is super easy. So let me see the matrix. Okay, so you can directly compute the AUC score, right? And you can use precision. This is precision score, and you can have the F1 score. So there are a lot of them. Okay, so you can also have another precision recall curve. This is another curve different from ROC curve. Okay, so you can have all kinds of things like specificity. I'm not sure whether. So basically the metrics are all defined here. Okay, so ROC, right? So ROC curve, right? So for ROC curve, keep in mind that we have the scores, right? So these are probabilities, right? Because the probability can be the probability here, then you will compare with different threshold and it will plot a curve. Okay, so this is the probability. Okay, Otherwise, for other like a recall or precision, the true, ground truth, and this is the prediction. Right? This is 0, 1. Okay, this is the probability of it being 1. Okay, so there are differences. Okay, this is second learn. In the next assignment, we will look at second learn. Okay, so if you don't know second learn, your coding is slower because you need to write those functions to count true probability, false probability stuff. Okay, and there's also, you know, these are also in TensorFlow, for example. TensorFlow also has a matrix. Okay, so the reason of TensorFlow is because it want to take the derivative of those matrices. Right? So you need to use TF or something. Okay, and all these matrices. So yeah, these are the side note if you are interested in coding. Right? So otherwise, this is a different kind of loss. Okay, accuracy. So I believe there's also like a mean square error. Okay, all the metrics. So, and we will look at hinge loss later. Okay. Yeah. So we kind of go a little bit far away. Let's come back. Okay. So here we are just assuming 50% is the threshold, right? Which makes sense. Right? So if one is 60%, the other is 40%, you will choose 60%, right? Unless you really care about safety, right? You want to have really low risk to approve a predicate. Right, so 1 minus max is the actual mean of them. Right? So this is equivalent. Okay, so probability error is mean of them, because we will always assume the larger one is the less. Any questions so far? Yeah, so for deep learning, you will use TensorFlow, Keras, and PyTorch. Okay, we will not cover that. We will focus on second learning in this course for hands-on. Okay.
What does the given x? I'm sorry, go back. What does the given x represent?
What did what?
Yeah, the first conditional statement, like with probability c equals 1 given x. What is that x in this case?
You mean this x?
Yeah, that's right.
Yeah, this is 2 attributes, income and savings. Okay. Based on that, you will have a function theta x mapped to y, right? So, but here the y is the probability. Okay. Based on this probability, you predict whether it's 1 or 0. Okay. Peyton, is this okay?
I'm kind of lost on the connection between like c and these two events.
Oh, c is just y. Y is because of the calculation, right? Y is either 0 or 1. Y is c, basically. C means class. Okay. Because
So is it
this classification. It's okay?
So is it predicting 1 for both x1 and x2?
No, x1, x2 are the input attributes, right? Remember, machine learning is y equal to fx, okay? But here we will first predict the probability p equal to fx, okay? And then based on the p, we see whether it's a positive or negative. If p is more than 50%, then we think it's a high risk, right? C equal to 1. If it's less than 50%, we assume it's low risk. Y equal to 0. Is okay?
So the threshold value, Professor, 0.5, are we setting it ourselves or?
No, here we are just using 50% because we only have 2 classes, right?
C is our decision, right?
C are what?
C is our decision, right? Our decision.
C are Y.
Yeah, why is the decision here, right? C is 1 means we are decided.
C is not
rejected. Not
C is a high risk or low risk. Based on high risk or low risk, we will take the decision. Okay.
Okay.
Equal to 1 is high risk. Okay. So we are using C because C is classification, right? So we just want to say this Y is classification C. Okay. Okay. So 1 is high risk, 0 is low risk. Based on that, you can take your decision. Okay. Yeah. And yeah, let's continue. So next, is there any questions? All right, so let's continue. Yeah. So next is very important, right? So we have the Bayes rule. Okay. So what is the Bayes rule? Right. So because we are talking about the Bayesian distribution theory, right? So Bayes rule is something like this, right? So basically, we know that in probability theory, right? So what is PAB? Let's say we have A and B2 events. What's the probability that PAB happens together?
If A and B are two independent events, it's P of A into P of B.
Yeah, if they are independent, you have P of A times P of B, right?
Yes.
Yeah. But if it's not independent, what will it be? Let's say B
P
is,
of A, conditional probability times B, I think.
yeah, exactly. So you have this, right? So P,
A over B,
right,
B
like,
over A.
okay, right. So either way to remember this is you think about it like taking the product. Okay, so this is the probability series stuff. Condition. This is how conditional probability defined. So I will not go through it. Okay, otherwise we will take forever. Okay, let me see why. Yeah, so maybe I should still pull this in. So this is how conditional probability defined. Basically AB divided by PA. Okay, is conditional probability. Okay, I will not go through this stuff. Just to help you to remember this. Okay, so basically you think about A times BA. Right? This cancels, right? So it becomes B. But no, this A will be put here in probability. Okay, this is easy notation. Remember. Okay. We can also have a symmetric one, right? So we first consider we have a condition, which is first we consider B, right? And then based on B, we have A, let's say. So we first have B, and then we have A, okay? So both are fine, right? So now you should be able to understand this posterior probability. Later we will look at why these names, okay? First we describe using the formula here. This is the Bayes rule, okay? Basically, if you think about this times to here, right? So this thing is what? This is P X C, right? Both, right? This is X is at the bottom. It's also P C X, okay? Right, they are the same. Both the NX happen. Any questions? I see a question. Yeah, so if you have any question during the break, you just let me know. Okay, so we will answer questions during the break on the assignment one. Okay. Now let's focus on the class. Okay. Yeah. So you can see they are actually equal, right? So this is basically Bayes formula, basically. Okay. So this should not be what we are talking about. This is basically probability series stuff, right? So this is okay. Actually, just look at here. Okay. So this is Bayes. Okay. BA times PA is actually PAB. That's it. This, if you time to the left hand side, it's also PA. Okay. Yeah, see another chat. Yeah. So yeah, but what's the point of this, right? So it's not so interesting unless we give them meanings, right? So let's give them meanings, right? So remember we have the X, which is the data we see. So we see the X1, Y1, right? In machine learning, X2, Y2. Right? So these are the data we see, okay? The training data, these are the X, okay? And maybe we can just focus on particular X first because the mapping is on particular data X2. Right? This is actually just X because C is 1, okay? So based on the data you see, right? So this is the data you see. This is the actual class, positive, negative, okay? So here we can give some meaning to them, right? So this is called evidence, right? Because this is X is what you see in the training data. This is the evidence, okay? By the way, if you can just ask your question directly, that will, oh yeah, so the devices are on their way. Okay, I will get the device when BJ, our technical staff, tell me it's right. Okay, I think maybe 1 week or 2. Okay, right now let's use this. If you have any difficulty, just let me know. Okay, so evidence is because you see X. Okay, this is evidence of you see this, right? Probability. This is a constant because this is the data you see, okay? And the C is the prior, right? How many classes you have, 0 or 1, okay? Right, so this is the prior, P1 or P0. Okay? This is how likely, maybe most people are not high risk, right? 99% are low, 1% high risk. This is called a prior, right? So P, C equal to 1 is only 1%, okay? P equal to 0 is 99%, okay? If you have difficulty understanding my handwriting, just let me know.
Yeah. Professor, I have a question here.
Yeah.
P of X, there is this probability of sample. It means that the probability of the instance, right? Then how could we calculate the probability of the sample in the real life?
Oh, so this is what we do. So we assume there's a probability, but we don't know what the model is, okay? We assume there's an underlying distribution there, but we don't know what's the distribution, just like the sign we see before, okay? Yes, this is our assumption. There should be a rule to generate the data X, but we don't know what's the rule, okay?
Okay.
Yeah, so, but if there's a rule P there, then we will have this requirement. Okay, so this is a basic assumption of Bayesian, okay? Maybe it's a little bit difficult for you to understand now, but it just works. This is how people do it. Okay, so yeah, so basically this is the evidence. Basically you see these x1, x2 values, maybe 10 of them. What's the probability that you see that, right? So actually there are some probability, right? So for example, if you see, if you go back to the previous example, right? If you see somebody have a lot of income, also a lot of savings, probably high, right? If you see somebody have, let's say, a lot of savings, but almost no income, it's going to be a little bit lower, right? So if you see somebody with an income that is, let's say, very big, 1 million, right? And the saving is 0, it's even lower, right? So if you are keeping making money while you don't have any saving, right? So there's some distribution there, but we don't know what exact distribution it is, okay? So this is assumption. So there will be some P. Actually, we don't care about them. We'll explain later, okay? So these are what you see x1, x2. What's the probability, right? And this is the prior. I think because one student has some concern about handwriting, we can do something here, okay? So basically, we are saying that we have let me see how to say this. So for example, in our previous example, the high risk is only 1%, right? So then we have something like this. Okay, 1%. Okay, this is prior. We already know some bias, right? So let's say this is the prior. Okay, this is what we know about the. Oh, let's do 9. So this is what we have here. Okay, you look at the bottom. Okay, this is actually impact your data. The prior actually will influence your prediction, right? Let's say if most of people are, for example, if you don't have any evidence X, right? Then you will usually, it's safer to assume this customer is safe, okay? Otherwise you will not make any business, right? This is also the same if you are looking at students, right? So, and maybe for computer science, most are male, right? So their prior do have some bias, okay? Which will impact your prediction. And how to impact the prediction by using the Bayes rule, okay? So here is the prior, and here is the evidence, what you see, okay? And here is our actual model that we are modeling, okay? So if you know the prior class, right? So let's say this is the high-risk people or low-risk people. What's likely you will see the attributes, right? So this is a generic process, right? You know the ground truth, this is a bad guy, right? So then how likely you will see its savings and, income, okay? And finally, this is called a posterior, right? So let's look at the relation. Evidence is the data you see, okay? Prior is without seeing any evidence. What's the distribution? Okay, this is again a PML, okay? This is NPM. Okay. And the likelihood is a general process, right? You know your class. How likely you belong to this class? How likely you will see a distribution of your income and you know, the savings, right? You can expect for bad guys and the good guys, there will be very different distribution. Okay, maybe the bad guy don't have any income but a lot of savings because, like they just do something else. Okay, right? So and finally the posterior, right? Posterior is relevant to prior, right? So prior means, hey, previously I believe something like this. Okay, I believe something like this. Now, if I see the evidence, I see this guy's income and you know, attributes, something like this. Right? So now let's say if I see something, I see some X. Okay. Now this will change my belief. Okay. Maybe now my belief becomes totally reversed. Right. So this now I will change to this belief. Okay. Right, so 80%, 20%, because I see this guy's attribute, right? So the reason we change it because we see that, okay? So this rule basically tells you, right, initially you have some belief. Now you see this guy's information, right? So in the database, right? So now how likely will change the belief that he is a good guy, okay? So, and the key is we want to model this properly, okay?
Professor?
Yeah.
Where the prior is dependent on the sample we have collected, right? If the sample is biased, then obviously the answer would be tilted to always the posterior will be tilted to the high bias, right? Then,
if your collection is biased, then prior will be biased. Okay. Let's say you have 100 men, 100 women, and then if you run a sample, you expect the prior should be not biased, right? But if you just sample from those people from computer science, right, for example, then it will be biased. Okay. So your training data, if it's not reflecting the ground truth, then you can learn nothing. Okay.
Okay, Professor.
Yeah. Okay, some useful property to know, right? So one thing is that you know, let's say the probability of 0 and 1 sum to 1, right? So another is this one, right? So this one is not difficult to see, okay? Because yeah, let's go back to the because of the handwritten issue. Let's go back to here so that it's not concerned. Okay. Right. So here we have this. Oh, actually, it's a reverse. So, okay, so this is kind of C equal to, okay. What's this equal to? Can you simplify this a little bit? Anyone? By the way, so this is actually a vector, okay? So as we discussed, so this actually equals to the joint probability, right? So that you see both, okay? So you see X, this attribute, and it also belongs to the, it's a better guy, right? So basically you have the condition times this, right? So this is the base rule, okay? This is conditional probability. The base rule is the other one, okay? So this is the base rule, okay? It's based on conditional probability, okay? So because of this reason, now you can see the left-hand side and the right-hand side, you know, this thing is this, and the second one is actually right. So the second part is this, okay? This thing is this. Now it's not difficult to see that if you sum them up, okay? You sum them up, you got PS, right? So these two conditions are ordered, right? So if we pictorially plot what this means. Okay, so this means that this is the union set. This is the order set. Okay, right. And in this case, if let's say you have two classes, right? So this is union Venn diagram. Okay, this is C equal to 1. Okay, this is C equal to 0, right? And in some portion of it, right? So you have X. Okay, this is X. Okay, so if it's both X and C equal to 1, so this is this part. Okay, if this, it's this part. Okay, if you sum them up, of course it's X. It's X. Okay, so you can easily see the Venn diagram. Okay, any questions? Yeah, okay, then let's continue. And so the next rule, okay, we have this rule. So this is saying something like if you have a condition, okay? So this rule is something a little bit different. Okay, let me plot it. So this is saying you can add any condition. Okay, so for example, if we have this Venn diagram, and this is 1 plus this is equal to 0, okay, and this is X, right? This is X, okay. Now, depending on X, what's the probability you have C equal to 0? This is this percent. Maybe this is 40%. That's 60%. Okay. This is depending on this X. What is this thing? Right. So this is maybe 40%. Okay. And the sum of 100%. Okay. So that being said, so you can add any additional condition there. The rule still holds, right? Because you are just dig out a even smaller condition, right? And then you treat this as a whole set. Okay. And based on this condition, it's like you can treat this as a whole set, then you look at the others, just following what we said. Okay, it's still holding, right? Any questions?
Yes. The first one and the third one, they're both the same, is it? Aren't they?
Yeah. So this is the same as this basically.
Yeah.
Other than that, your union set now becomes X. Okay. Yeah. Originally, you're considered a big union set. Now you only consider X. Right? And this, you consider 1 and 0. Originally, you are saying this 0 and okay.
Yeah.
Yeah.
Thanks.
Yeah. These things are not that important until you look at more complicated, graphic models. Okay. So there's a lot of derivation, like common filter, those kinds of things, which we will not cover unfortunately because of time limit. And you can take a look at I think the textbook recommended pattern recognition and machine learning. Okay. And so yeah, Bayes' rule for the general case, right? So previously we only talked about two classes, right? 0 and 1. Okay. But for the general case, we have this. So this is still the rule, Bayes' rule. Okay. And keep in mind, we are always talking about K-mutually exclusive and exhaustive classes. Exclusive means, you have 0 and 1, they have no overlap. Okay. Exhaustive means if you union them up, that's all the possibilities. You don't have a new class that is not considered. Okay. So mutually exclusive is very important. Okay. And because this is our assumption, right? So we are not considering multi-class labeling. Okay, multi-class classification. There are problems of multi-class classification. Let's say you have an article, you say this is news and sports, right? So, and something else, right? Politics and sports, right? So you can have multiple labeling. But here, you can either belong to class 1 or class 2, but not both. This is our assumption, okay? And if this is the case, right? So you can write it further like this, right? So you can write it like this, okay? Basically, we are saying that this thing is equal to this thing, okay? It's actually not easy, not difficult to see, right? So why? It's just due to this rule. Okay, now you don't have just a 1 and 1, 0, 0. You have 2 and 3. Right? The C equal to 2, C equal to 3, 4 classes. This thing is still PX. Okay. And you can also pictorially think about it using Venn diagram. Okay. And actually, if we have these probabilities, right? So if we have these, okay, these probabilities for each class, okay, based on the data, you can, for class 1, what's the probability? Class 2, what's the probability, right? So what's the optimal decision rule? Of course, you want to pick the ones that are the most probable, right? So this gives us this, right? So you will take the most likely. Let's say if you see this saving and you know, salary, then class 1 is 70%, class 2 is 90%. Of course, you prefer class 2, okay? So, and they don't have any relationship, right? So you can belong to C1 and C2. You don't have to sum them up to 100%. Oh no, I mean you still have to, right? So yeah, because it's a mutual exclusion, right? So basically, maybe one is 50%, the second is 20%, another 30%, right? So you will pick the most probable. Okay. And this is the case even if there's no majority class, right? If one is 10%, another 5%, the other all 5%, then you will pick the 10% class. This is the best guess, right? And another important thing to keep in mind, you don't care about this, right? When you care about C1, C2, C3, only these things on the top chains. This is the same, okay? So you only need to care about this part, right? Where you have prior and also the generative probability, okay? Any questions? So this is for if you have more than 2 classes. Okay. Yeah, so then losses and the risks. Okay, so let's go through a little bit of this and then we will take a break. Okay. So in general, different decision actions may not be equally good or important. Okay. So for different, let's say we have different classes, right? So and we also have different actions. So here's an example. Okay. Let's see whether we can. No, it's not a grid like this one. So basically, so you have actions, which means decision to assign a class to a class CI. Right? So basically, you can say something like this. You have, let's say this part is action, okay? And this is the actual class, right? So if, no, it's a little bit difficult. So let me see how to plot this. Okay, let's take a look at it. So let's say we have a action, right? So we assign an input to class 1, class 2, class 3, right? We know that one of the class is the best, okay? But we can assign to any of the class, right? So this is the action, okay? Right. Associated with each action, we actually have a loss. Right? For example, if we have a COVID-19 patient, we assign to normal, maybe we will get a penalty, a loss of $100, right? If we assign a COVID-19 patient to COVID-19 patient, so we will get a loss of 0, right? There's no penalty, okay? But if we assign a normal people to COVID-19 patient, right? So that may be not 100 penalty, maybe $2. Right? It's not good. That person may be quarantined, right? But there's no, you know, there's no virus pandemic issue, right? So you can give different loss to different actions. Okay. So action I means you give to class I. Okay. While the actual class is K, right? So there's a loss between. So you have the predicted class, you have the actual class, you have a loss associated with it. Okay. So now, what is the expected risk for taking action alpha given input? Right. So the expectation is this. Okay. Can you see this? Do you know why? Yeah, if not, let's take a look at what is expectation, okay? expectation is like a mean value, right? So this is expectation, okay? So if you have, let's say we consider discrete probability, okay? And you have, you can take a x1 with probability 1, x2 value with probability 2, okay? Xk with probability 2, right? So expectation is this one, it's okay? Now here we are taking expectation because, you know, this is the probability, okay? This is the P1, P2, P3, okay? And now the loss is here associated with K, right? So this is saying your actual state is K, right? And what's the probability that if you see your data, the actual class is K, right? So maybe for C1 is 20%, for C2 is 70%, 70%, C3 is 10%, right? For each of them, you are associated with a risk, okay? A loss, right? So the expected risk is this one, okay? So just treat this lambda, the loss, as X here, okay? Which can take different value and the different conditions. This P is this P, okay? Then you can see. Okay, so the optimal decision rule just say that you want to take the particular action, right, that lead to the minimum risk, right? So action basically assigned to class I, right? So this I is whatever it is, I just assigned to class I, right? And for different actual class K, then you have different risk. Then you take an expectation, okay? And you take the minimum risk. Okay, so I think the time is almost there. We will take a break for 10 minutes, and we will come back in maybe 6:20, and we will continue with the slide. Today we will finish this slide, and we will also go through some mathematical backgrounds, okay, to prepare for the next lecture. Okay. All right, so if you have any questions, just like some student asked earlier in the chat, feel free to ask me. I will be on.
Professor, I have a quick question here.
Yeah.
I'm a little bit confused about the expected risk as well as with loss. What I've understood is that if, let's say, we have two classes, risk and low risk. If we incurred one, if our decision is one class, let's say low risk, low, then there will be a certain amount of loss corresponding to that decision. Likewise with the high risk as well. Then I'm somewhere not getting connected with the expected risk. I mean, can you give some more intuition behind the?
Oh yeah. So for example, if you have patient, right? So let's say you have the COVID-19 patient and a not COVID-19 patient. Okay. And then this is your prediction. Okay, you predict as a COVID-19 patient, not COVID-19, right? If it's COVID-19 patient, you predict COVID-19 patient, you take the proper actions. It's no risk, loss is 0. Okay. Right. If it's not a COVID-19 patient, you take you think he is not a COVID-19 patient, it's 0. Okay. Right. If there's a COVID-19 patient, right? So and you think you reckon as not COVID-19 patient, you should be fined $100. Okay. Because you can, infect others. It's a lot of issue. Okay. And if this guy is not a COVID-19 patient, but you misclassify it as a COVID-19 patient, right? It is a loss is maybe $2. Right? So this does not infect others, but it will cause inconvenience for this person. Right? He has to quarantine himself for 2 weeks for them, right? Is this intuitive?
Yeah, I'm getting this, sir. But the expected risk, I mean, it deals while we are training the model, or I mean, let's say the Navy space example. How does this?
Oh, this is basically saying this, right? So based on my features, let's say the fever or etc., we have a bunch of features, right? Then we may have certain probability to belong to C and N. Okay.
Given X, what is the probability of being into that class? That's what, right?
This is the model we will predict. Okay. This P is what we will learn in the next few lectures. It's okay.
Okay.
Yeah. So this is the machine learning model. Okay. Yeah, we are talking about in the abstract level. It's okay.
Okay, Professor.
Yeah. And once you have this, right? So now, but you let's say if you think you will predict as C, right? So then you need to take expectation of the risk. Okay. Right.
Okay.
So we are taking expectation over these items. Right? So there are different probabilities associated, which you can predict based on X. After we talk about how. It's okay.
Okay, Professor.
Yeah.
So, Professor, if my general intuition is that we want to reduce the expected risk because it will make our model more optimal.
Yeah. So you know, so because
yeah, sorry,
it's a balance issue, right? So for example, if you have some critical action, right? So you think this person is not COVID-19, but he has COVID-19, right?
Right.
You give a high risk, high loss. Okay, then it will try to avoid that case, even though sometimes it will detect more non-COVID-19 patient as COVID-19 patient. Maybe we will tolerate that. It's okay.
And since it's just an optimization thing for Bayesian.
This is the preference. Okay, so these weights. Okay, these weights are hyperparameters. It's okay.
Hyperparameters.
Yeah.
Okay.
Yeah. For example, if you look at yeah, so these are user defined. Which one you want to put more emphasis, which one not. Okay. Scikit-learn. Yeah. So maybe I should put it clear. This is hyper. So scikit-learn. Let's just look at it. Support vector machine. Okay. Right. So you have something called class weights. It's okay.
Yes, sir.
Yeah. So the class weights is saying that if you have COVID-19 patient, probably you care more, right? So so this is computed based on the class weights. Okay, so basically the class weights, this is the variable. So if you look at the, right? This is the hyperparameter to put to the model, then it can fit. Okay, so basically, so if you have COVID-19 patient, which is not many, but you should give them high weight. Okay.
I see. Yes.
Yeah, because you know, otherwise, if you 99 people are not COVID-19, you just assume it's always not COVID-19. You get 99% accuracy. Okay.
Right.
Yes. So this if you use by default, it's a balanced mode, right? So if you don't specify this parameter, scikit-learn will treat the balanced mode. Okay. Which means it will adjust it based on your sample number. Okay? If you only have 2 COVID-19 patients, right? So it will assign larger weights. Okay. Using some frequency, you know, it will adjust this, right?
Right.
So this formula, maybe they think this is the best. Okay, this is not just for SVM. Every model is doing this. For example, look at even for decision tree, let's say. Okay. You have this. Every scikit-learn model has a class weights. Let's see. Right here. Okay.
Right. Right. Yes, sir.
Yeah. By default, it's not using class weights, by the way. Okay. It's defaulted now. Right. You can give a balance. Okay. If you give a balance, it will use some formula to compute. It's okay.
Yes. Yes. Yes.
Maybe this is not the best. So that's why you can assign your own weights. This is a hyperparameter. Okay.
Gotcha. Yes, sir. Yes, sir.
So yeah. So in our case, for example, because scikit-learn want to make things a little bit easier to manipulate, right? So so it's a one-dimensional vector. Right? We have two-dimensional like a matrix. The one-dimensional vector is more like, so you only have the true class, right? So the C1, C2, C3. Okay. And if you have the true class, and then their lambda is all the same. Let's say you think this is 3, 3, 3. Okay. This is COVID-19 patient important. This is a healthy person. Right? Okay. We are talking about more general. It's okay.
Okay. Yes.
Yeah, we can have the different mapping to COVID-19 with different. Okay.
Yes, sir.
Yeah. All right. Any other questions, especially about the assignment?
Yeah. Professor, can I share my screen?
Let me try to. Let me see. Yeah, I can, but I lose my mouse. This one. Okay. Yeah. So Mandroid, right? Who just talk? Oh, okay. Yeah. Let me make you a co-host so that you can share. Okay. Now, please go ahead. Manuel, yeah, you can say.
So here I'm getting confused. So I think this is the nut, and this is this a washer or?
This is a nut. This is also a nut, right? Washer usually here, right? You have a washer.
Okay, so this is also another nut, or?
This is lock this nut. Yeah, I think it's another nut. Yeah.
Okay, and this is the thread. And one more question is like, is this also a thread, or what is this called, Professor?
This is a thread, but you can ignore it because it's not strict, right? So we are not considering this case.
Okay.
I think it's a try to lock it, so otherwise there's something, it can easily flip out. So kind of bend it a little bit. Okay.
Okay.
Yeah.
That was my question.
Okay. Thank you.
Professor, about the assignment, can I also share my screen for one particular image? Maybe you can give some introduction.
Yeah. Okay. Yeah. Go ahead.
Yes, sir. So with this particular image, can you see it's a ocean of nuts and bolts? So I don't know.
Well, yeah, you're unlucky, basically. Then in that case, let me see. Because we are randomly assigning images to students. So if you this is the entire image, or this is just the zoomed in part of it?
No. So this is entire image, sir.
This is entire image. Oh, okay. Can you? Yeah.
Oh, sorry. It's
okay. So you can use this to control clip, actually. Can you zoom in a little bit? Let me see.
Yes.
Yeah. So my understanding, this part definitely important. Okay. This part I think it's also relevant. This, if it's too many, it's go beyond 100. You can ignore this. Okay.
Yes.
Yeah. So these are obviously the most important because if you have a drone here, yeah. So again, you need to inform the gas. If it's go beyond 100, you need to prioritize. Okay.
Right. So also, these parts, do I?
Yeah, this is at the bottom. You don't care, right? So when you fly drone, you really look at it. Okay. Otherwise, you have something here. You don't care, right? Otherwise, you have to do all of them. Then that's great. Right?
Okay. Thank you, sir. So this is the only image I had an issue with. I understand. Okay. Thank you, sir.
You're welcome. Let me see. I see another question, but let me see. Oh, so maximum number of annotations. Usually we will not go beyond the 100. I know a lot of the simple images are like 10, 20, 30. But if you are unlucky, you get the image like Sami you got, you can consult me or the TA first. Okay, we will see how which are more important if you don't know how to judge that. Right? So that's a safer choice. Okay, we don't expect you to annotate them like 150 or 200. That's good. So the main purpose of the assignment is to get you familiarized with the tool. It's not easy to use, especially if you zoom in, zoom out. Right? So you need some amount, right? So, but if you, let's say I'm most 100 per image and you have 10 images, you have 1,000 of those experience, then basically you are familiar with the tool. Right? So that's the purpose, okay? Did I answer your question? I see manually, I think. So, yeah, we only have 2 minutes. If you have a question, please feel free to ask.
Oh, I have a question.
Yeah.
So in the assignment, like instructions, you had both the ID and then the description next to the ID, and they were both the same. So like if the ID was head, the description was also head. Is there a way to add these descriptions after you've already made the annotations?
Oh, description, I believe it's not important.
Okay, so I can just not worry about that as long as the ID is correct.
Yeah, just care about ID. Okay. Yeah, you don't care about the description. You can add anything.
Okay, because I just left the descriptions blank.
Yeah, because I think I have to export it. Description is not there. Yeah.
Okay, I was just making sure. Thank you.
You're welcome. So if you want to see the description, you need to save as workspace. Okay, the annotation will not save it. All right, any other questions? Again, if it's because of the delay of the access to the folder, talk to the TA. Okay, we will permit the number of days of delay. We can extend those days. But pay attention because we will probably release the second hands-on assignment very soon. Okay, maybe this Friday or even Thursday. we will see. If a lot of students are delaying, we will try to make it Friday. Otherwise, probably Wednesday we will release it. Okay. So you don't want to have assignment overlap. Right? So originally we will release it on Thursday. I was thinking, but maybe I should release on Friday because you know, a lot of students are not submitting by Wednesday. So the scikit-learn experiment is the most important, okay, because you know, for machine learning, so this is a key library. Okay. Unless you want to implement everything yourself. Okay, so let's continue. Unfortunately, it's 10 minutes already passed. Okay, so yeah, so let me see. No, this is a little bit difficult to handle, right? So we will think about a simple case to make some intuition. Okay, let's just think about the most simple case, right? Just like what we said, right? So if you have a covariant coefficient and you predict a covariant coefficient, there's no loss, zero. Okay, if I and the k is the I is predicted class equal to the actual class, then you have no loss, right? If your prediction is wrong, that's where you have the loss. Okay, you have the penalty. Okay. Some penalty should be big, some is small, right? But here we just assume all are one, okay? In that case, the expected risk, right? So this is the formula for the expected risk, will become this, right? So it's a really very simple. Right? So if you look at the k classes, right, in the sum, only one of them are equal to, you know, I, right? So if equal to I, because this lambda is zero, then it will become, this term will become. For the rest of the terms, it's all, you know, because this term is one, it's all zero. Right? So you are summing k minus one items. Right? The only item that is not in the summation is when they are equal. Because this is zero, this term is one. Okay? And another way, because you know, all the k terms sum up to one, right? So you have one item gone, then the rest of the sum is one minus this item. Okay? So the risk is equal to one minus the probability, you know, posterior probability of C, okay, by UCS. And this is only true when we use this simplification. Okay. And the optimal decision rule, remember we talked about optimal decision rule. What we want is with the minimum risk, right? We want to choose a class I with a minimum risk when we see X attribute, okay? So this is equivalent to we want to choose the maximum probability, right? Because we want the minimum R, we want to maximize the P, right? Because it's a negative, okay? So basically what we are saying is that this minimum R and the maximum P are the same, okay? Which only holds if we have this assumption, okay? Any questions here? Okay, now let's continue, okay? Reject option, right? So in certain cases, you can reject a class, right? So you can say, hey, I don't want to make a decision, right? So here the loss function will become something like this, right? So if your class is you know, I equal to k, by the way, you know, we will take attendance after this slide. Okay, this is a reminder. So I see some students left just now. So unfortunately, okay, so we'll sample some. We will not take all the students. Okay, so if I equal to k, then our weight is zero, right? Because we have no loss. Okay. Otherwise, we will think you know, the loss is one because our prediction is wrong. Okay. But there are certain cases you will not make a decision, right? Whether it's truly k or not, right? So it's truly I equal to k or not, right? In that case, you reject. We should have a penalty that is in between 0 and 1, right? Because I'm not certain, right? So it's better than you make a wrong guess, right? It's like you are doing an Excel lab, right? You have a question, right? So you say, hey, I don't know how to do that. That's better than, hey, you make a wrong answer and pretend you know it, right? So that's why we have the lambda in between, okay? And based on this lambda, we will have the expected risk, but let's just take attendance. Okay, this slide is gonna finish.
I have a question,
Yeah.
Doctor. Yeah. This K, the second case, if I equals to K plus 1, that K is same K or it's a capital K there?
This is a capital K. This is a capital, you know, you have class 1 to K, right?
It's a different,
We use a K plus 1 to mean the rejection option, okay? This is not a true class, right? We only have 3 classes. It's okay?
Okay.
Yeah, so this is just a notation.
Right? Oh, this is not this K here.
Yeah, it's any number that is not 1 to K. You can use it. You can even use 0. Okay? Yeah, we just want to say this is a rejection. Yeah. So let me take attendance. Before that, let me see. So what else? Yeah. So let's take some rejection option in effect. Okay. So and then we'll take attendance. For example, we have K nearest neighbor classified. Right? So we can take a look at. I believe there will be some examples. So. Okay, so here's an example. Right? So this is the nearest neighbor classifier, which means you will remember the data, okay? And then when you see the new attribute, x1, x2, you see who is your closest point. Let's say this is the closest point, I think I'm right, okay? Right? So, you know, so if I'm here, the closest point is blue, okay? In that case, there's no ambiguity, right? But there's a case that if you have 4 or 5 nearest neighbors, right? So what happens if, let's say in this point, right? So I look at my nearest 5 neighbors, okay? And I find that, let's say 1 is red, 2 are blue, 2 are green, right? So what do you guess? Is it blue or green? You don't know, right? So you can reject. It's okay? Any guess could be 50% wrong, blue and green, right? So in that case, you can have this white part, which I don't make any decision, okay? Any point fall in this area for x1, x2, 2 attributes, okay? I don't make any decision, I reject, because these are the rejected, okay? So that's an example in action. Okay, now I hope those people who left have friends telling them to take attendance. Yeah, so what I will do is I will sample some name and then mark all present. Okay, so then I will sample and I call your name. If you are not, you unmute yourself and report yourself. Okay, and you can say here for them, right? So I will check your name, by the way, on on attendance, right? So when you talk, your name will pop up. Okay, and if they match, I will keep the tick. Otherwise, I will take a cross. Okay. Yeah, let's continue. Sumant. Sumant. Unfortunately, okay, so Havana.
I'm present, Professor.
Okay. Chun Yao. Chun Yao Chen.
Yes, I'm here.
Okay. Daniel. Daniel. Daniel.
I'm here.
Okay. Linan. I see some.
I'm here.
Okay. Annie.
I'm here.
Okay. Yan. Right. Is this the right?
I'm here.
Okay. If I pronounce the name wrongly, just let me know. Okay. Emmanuel.
Here.
Okay. Saidipa.
Here.
Chloe.
I'm here.
Hello. Okay. Nancy.
Here.
Okay. Fruitville, maybe. Fruitville. And Ran Yan.
Yes, I'm here.
Okay. Isan.
Here.
Okay. Ming Yong.
Yeah, I'm here.
Okay. Staff. Staff Saeed? No? Yeah, so in the future, we will use this sampling because otherwise, it's too time consuming. So I see somebody coming and I see a chat. Let me see. Oh, okay, I see.
Hello, Professor.
Yeah.
I got disconnected. I just connected back. My name is Prithvi.
No worries. Okay.
Thank you.
You're welcome. All right, so let's continue. I see another chat. Sumet. Okay. All right, so yeah, let's continue then. Yeah, so there's a rejection option. So basically not anything in between. Okay, 1 to k. And so here, what's the expected risk? The expected risk should be something like this. Right? So you think about it. If you take the rejection option, which is k plus 1, right? So what will happen is that you consider you still have only k options, right? K possible scenarios, each with this property. Right? For each of them, because you take a rejection, the value associated with that will be that, right? And then you just compute this expectation. And because the sum of those probabilities is 1, so finally you get that. Okay? So this is the expected risk, which is lambda, if you take the rejection option, right? And on the other hand, if you take a regular option, right? So you assign a class I, right? So this is what we just derived, okay? 1 minus that probability, okay? This is what we just. So if you want to refresh your derivation, it's okay. Again, you'd better go back to the slides and take a look. You cannot have too much time stop every slide. And if you have any question, just stop me and ask. Okay. The optimal decision rule says that we want to do something right. So for the risk, I want to choose a class with the smallest risk, right? So this gives a natural choice, right? So now, besides the k classes that you can choose, of course, you will choose a minimum of them, minimum risk, right? You also have the rejection option, right? So the rejection option, basically, if the rejection option risk is larger than taking a minimum class, right? You will take that class, okay? If the rejection option is even smaller than all the classes, right? So you will take reject, okay? This is the optimal decision rule. And the equivalent form is this, okay? Right, so basically we are saying that, so why? Okay, so this is saying, risk and the P, we just derived in that special case that they sum up to 1, okay? So so this thing is equal to 1 minus this for regular option, okay? So this is a regular option, okay, for that the best class, okay? On the other hand, if you take a rejection, which is this option, your R is lambda, right? Your R is lambda, okay? So you basically are comparing this lambda with this 1 minus P, okay? So you only choose CI if the lambda, which is the penalty for the rejection, is larger than this, right? So if you adjust a little bit, you will see that PCI comes to here and larger than 1 minus lambda, okay, 1 minus lambda. You move lambda to the right, move P to the left. Here. Any questions? So this is basically, intuitively, it's also very easy to understand. So because, yeah, so lambda is a risk, right? So for if you take rejection, right? So if your probability is larger than 1 minus lambda, it's like this time you are looking like a binary classification. This is more than 50%. That's a kind of less. Okay. So because lambda plus 1 minus lambda is equal to. Zhen Ying, do you have any questions? Zhi Ying.
Sorry, I'm fine.
Oh, okay. This approach is meaningful only if 0 smaller than lambda, smaller than lambda, right? So because lambda is a penalty, right? So 0 is if you predict your prediction is correct, right? 1 is if you are making a mistake. Lambda in between, right? You reject. I don't want to answer. I don't know. I want to learn more, right? So it's better than you predict something wrong. Okay. And maybe when you reject, maybe it will be given to another expert. Okay. So if lambda equal to 0, we will always reject, right? Because if I reject, there's no penalty. It's like you make no mistake, but I will always reject. Okay. If lambda is larger than 1, right, I will never reject, because even if I give a random guess, right, the penalty at most 1. But now if I reject, I'm penalized more than 1. Okay. Finally, the concept of discriminant function, right? So we have seen that concept similarly, right? So the probability, right? So how likely you belong to class 1, class 2, class 3. Okay. We will take the most likely class. Okay. So one way to specify the classifier is through a discriminant function. Okay. So far we talked about the Bayesian decision theory. It goes through the probability theory. Okay. So there are two classic ways. Okay. One is, hey, you have X, you go through a probability, right? And then you go to a class. Okay. Another is directly go to a class, like logistic regression and a lot of other like deep learning neural network models. Okay. So when you go through the probability, you actually have a generative probability, right? If you belong to class, how likely you will generate X? Okay, this is called the generative model. Okay, this is called the discriminant model. Right. So there are different styles, and this you don't care that much about probability. Okay, this you basically first define a probability model, conditional probability, and then you do the model. Okay, and both have the discriminant function. Right. So if this for this kind of classifier, you directly define the shape of the discriminant function. Okay, for this kind of model, you need to define your discriminant function from probability theory. Okay, and we will see both. We will see the probability one in the next lecture, and then the other one in the lecture after. So for classification rule, it's very simple. Right? If you have a scoring function, right, for different class K, right, 1, 2, 3, 4, right, you want to find the one get the highest score, right? So so some ways to define the discriminant function. One is you can define the score as negative of R. But R is the risk, right? So when you maximize the score, you minimize the risk. Right? You find the class that minimize the risk. Okay. Another way is just to define the posterior probability, right? So how likely you belong to CI, right? So because the other classes have a lower probability. Okay. Another way is define this, but they are basically the same, right? So if you look at it, this is equal to this thing divided by px. Okay, if you split it. But because your data is given, right, training data is given, px is constant. Okay, so basically you are just comparing. These are the same. Okay, different by a constant, which doesn't matter. Okay, for different CI, the px doesn't change. Right? It's a constant when you compare different. Any questions? Okay, if not, let's continue. So for the two class case, it suffices to just define one discriminant function. Okay, so basically, you have two class discriminant functions, G1 and G2, right? So the score for class 1, the score for class 2. But in that case, you would have two set of function parameters, right? Theta 1 and theta 2. So why not just take their minus? Then you will have only one theta here. Okay, so this is actually also the special case about binary classification. Okay, for binary classification, we can eliminate half of the parameters. Okay, that's why you have, like, say, sigmoid or the binary cross entropy loss. Right? So for multi-classification, you have the regular cross entropy. Right? So let's take a look at this. Actually, if you have those concepts, you can easily use machine learning library. That's why we are mainly teaching the concepts. Okay. Libraries thing, I will leave it to the assignments and maybe a future like use. Okay, here build a math site. Okay, for example, if you have a binary classification, Keras has a binary cross entropy loss. We will see what is cross entropy loss later. Okay, maybe in the next lecture. Okay, but there's also categorical. Okay. This is more than 2 classes. Okay. Of course, for you know, this is TensorFlow carrots. Okay, for deep learning. Okay. Of course, you can also for binary classification, you can also use categorical cross-section, right? But that will double your parameter, right? So if it's a binary classification, we will usually use binary cross-section. Okay. So these are the small details that you might want to pay attention. Okay. Okay. So if we define something like this, how do we judge? How do we judge whether, for example, you know, belong to C1 or C2, right? So then you compare this new function, whether it's larger than 0 or not, right? So because when this gx is larger than 0, it means g1 is larger than g2, right? If g1 is larger than g2, you use class 1. Okay? Otherwise, if this is smaller than 0, smaller than equal to 0, right? So it means g1 is less than g2, you use c2. Okay? In that case, for this function, you are just checking whether it's positive or negative. Okay? It's equivalent basically, but you eliminate functions. Right? So previously you have 2 sets of functions, of parameters. Now you only have 1 set of parameters. Any questions? Okay, if not, let's continue. Right. So, and you have seen the k nearest neighbor classification. Right? So it's the same. Okay, for all the machine learning problems, you are thinking about x1, x2, maybe x3, and high dimensional space you cannot imagine. That's why in most of the machine learning textbook, you will only see 1 or 2 dimension feature like X. Okay, but in reality, you should think about very high dimension. Okay, so, and then for classification, you will have something like plus or minus. Here we have 3 classes: so circle, you know, square, and a triangle. Okay, it's not within the 3 dimensions. It's a 4th dimension, which is Y or C. Okay. And so what we are doing is that we want to define those functions, discriminant function. So that let's say, hey, this function says if you are on this side of the curve, it's class 1. Okay. If you are on this side of the curve, you're class 3. On this side of the curve, you're class 2. Right. And if here you are not clear, let's say 2 are green, 2 are blue for KN, you reject. Okay. So these regions are called the decision regions. If your feature, let's say ideally if you can compute this region, right? So then if you know the feature, you put it here, you know it's within this region, right? And then you just say, hey, this is here. If unfortunately your x1, x2 is here, then you reject. Okay? So these are actually defining the decision region. But in reality, you will not do that because no, these curves are difficult to describe. Okay? So you will still compute the discriminant functions and fix the max. Okay? Give a side note. So let's take a look at one case that you can actually get an intuition on that. So one example is the Verona diagram. Okay, so basically, what is a Verona diagram? This is like the skin of some fruit. Right? So the idea is very simple. Think about it. If these are the points, okay, right, and if these points are expand in equal speed, they will fit here, right? This is a perpendicular line separating them in the middle, okay. And here for these 2 points, you will have perpendicular line here, right? And here for these 2 points, you will separate here. For these 2 points, you will separate here. So inside this cell, if you have a point here, it's definitely closer to this point than this point, right? So because anything on the line is equal distance, okay? On this side of the plane, you are closer to this point. Okay? Now you know if you are in this cell, this means it's closer to this point than this point, right? So this is closer compared with this point. Compared with this point because it's on this side of the plane, right? So it's closer to this point than this point, right? So if you are inside the cell, it's closer than any point, right? So this is your closest point. Right? For nearest neighbor, you can actually keep those cells, okay? And then you just say, hey, if my coordinates fall in here, then I belong to this class, okay? Right? But in general, you cannot do that. You will just compute the function, okay? That's a lot faster. Okay, so basically, you just keep those k functions and compute it, right? This is even more convenient than this probability shape, okay? But the region is really saying that, okay, so my class 1 has the highest score. What are those coordinates? You plot them together. Okay? So each decision region corresponds to a class and may consist of non-continuous subregions. Okay? So this may not be continuous like here. Right? So sometimes maybe here there's another region. In the middle is C2. Maybe on the other side is C2. Right? So let me give you an example. So if you have do I have an example? I hope I can find an example. So let's think about these two Gaussians, okay, Gaussian distribution, right? And if we assume they are the scores, right? So we should think about, because this is flat, okay, this is flat. Then there must be more areas on both sides, right? Because the area of both are 1, okay? If you have more in the middle, then both sides are low, okay? So because of this reason, if you're on the very left side, the taller side will have a smaller value on the sides, okay? So this class will dominate. Let's say this is class 2, right? On this side, it will be class 2. And it's the same on the other side. But in the middle, obviously, these values are lower than these values, right? So in the middle here, definitely class 1 wins, okay? So you will have some region like class 2 and suddenly become class 1 and suddenly become class 2. So it's not continuous, okay? So this is a simple example to illustrate that. And the decision regions are separated by the boundaries, right? So on the boundary, it's like a C1 equal to C2, just like our previous example, okay? Our Bernoulli diagram, okay? Those boundaries are where you separate class 1 and class 2, okay? Class 2. Okay? But again, this is a very abstract concept, so in general, it's not so simple, okay? Like Bernoulli diagram. Okay, so that's for this slide, and we will take a 5-minute break, and then from 7 we will go through some mathematical stuff, okay, and to prepare for the next lecture. Okay, thank you. If you have any question, you can ask quickly.
I have a question, Dr. Yan.
Yeah.
Can I share my screen?
Let me see how to do it. Are you a co-host now? Let me.
Deepak.
Okay, yeah, please go ahead. You can share your screen now.
Okay. Do you see my screen?
Yes.
Yeah, it's I have a problem. I already completed the annotating, and I'd like to check again. This is my work I did and saved in CSV.
Okay.
And I wanted to load this on VIA again and to check am I right or wrong, or I can edit that, but I could not do that. How can I do that?
Oh, so you add files? Okay, so let me see.
This is, suppose I add file here, right?
Yeah. No, you add files. This is open project. Okay.
Yeah, okay.
You find
I add file here, then my file is, yeah, this is my file, CSV file. And if I do, then it says the requested image does not exist.
What? That's impossible.
Deepak, if you add the images there and you go up to annotation, there's an import annotation, and that's where you're actually going to put that CSV. At the top black bar, next to project versus annotation, one to the left, go down, import annotations from CSV, up one.
But I think you need to first export the images, right? And then.
Yeah, you're going to need to add the images back into the files as well.
Yeah, so I think you better add the images first.
Oh, does it work now? No, it's
have the image, so you need to
it's
add.
mal-informed lines.
No, can you refresh it?
Deepak, you need to add the image directory in your project setting. If you do that, then the image will show automatically every time.
Yeah, but I did already, this is my file. I have already completed my annotation.
Yes, but you still need to add the image files, not just the CSV. Both of them has to be added back.
Yeah. So
first of all, we have to.
Can you go to the CSV file?
Sorry.
Can you go to the CSV file you just showed?
CSV?
Yeah.
Okay. This file.
Yeah, just open it.
Okay.
So this CSV file is associated with the image file. Is okay? If you don't have the image file already loaded, it can be anything. These things doesn't make sense. It's unrooted. It's okay?
Okay.
This is the
that means first of all we have to load the image.
Yeah.
Oh.
Yeah. Can you go there? Yeah, just to follow the steps.
Yeah, I can do that. I can do from dot box. I can.
Let's do this and in your browser. Okay. You can just follow the steps. Yeah.
Okay, I'll do that. Okay. I think.
Yeah. Can you go to the browser right now? Yeah, can you go to that? Can you go to the software, the VIA? Just go to the VIA.
Okay, sorry.
I think it's just a HTML file. You can double click the HTML file. Okay. Yeah, can you do this? Just a refresh. It will create an empty space. Yeah, you see this refresh button?
Yeah. How can I replace all at once?
Let's refresh it first. Okay. You see this button I'm highlighting here? Yeah.
Okay.
Yeah, reload. You don't have this file now, right? So if your file is here, it should load. Okay.
Okay, BIA.
Oh, it's a compressed file. That's why. Okay, you need to decompress it. Otherwise, you can only use it once.
I got this.
Okay, now click Add Files. Okay. Click
Add Files. Okay.
Yeah, that's good. Okay. And can you select all the files? No, don't select this annotation file. Just select all the rest. No, click this image. Push Shift. Can you push Shift?
Shift.
Click this one. Yeah, push the Shift key and then click the ace. Yeah, you don't have to choose this way, but it's okay. Yeah. No, you don't choose this one. You don't choose this one.
This one,
not image. This is the folder. Okay. Yeah. Open.
Okay. Oh.
Now you import your annotation. Okay. Yeah. Go to
I can import now.
Yeah.
Import annotation from CSV.
Where's the annotation file? Why you have so many?
I had 20 last time, but I don't know. Where is my annotation?
Yeah, so this is the problem, see? This file and this file and this file are the same, okay? Right, so
yeah.
Yeah, because we just imported 10, right? So I'm not sure why.
The project file, not the annotation file. So that's why the image is repeated. So he imported the project file, which is also saved as CSV.
Oh, okay. So you need to. Yeah. So I think you are.
Can you export from JSON?
No. So what I think Sami is saying that when you import XCSV, you import something else which contains additional files, right? Sami, is this what you mean?
Project file kind of knows what JPEG was already there in the annotation, but it doesn't have the directory. So he was opening the project file, not the annotation file.
Okay.
Project file?
So project file and annotation are different, but both of them are saved as CSV. So that's the problem, I think.
Yeah, so you are not using annotation file, you're using the project file, basically. Right, so no, you need to import annotation file. Okay. Yeah, anyway, I think the TA has an office hour. Yeah, so, and you can also make a appointment with TA, or you can contact Sami, right? So, and try to get
Okay, thank you.
Yeah, because, we are beginning. Okay, thank you. Yeah. Okay, for this slide, I already shared, I believe I already shared on Canvas. Okay, so the multivariable calculus, right? So, and yeah, let's go through this. Quickly, and then that's the end of today. Okay, so we all know that machine learning is not just y equal to fx, right? So it's not just a you know, a scalar, right? So x and y are not scalar. Right? Like say x can have x1, x2, and sometimes y can have additional attributes, y1, y2, y3, right? So for example, we have the bounding box for the object, and then we have a label, right? It's a cat or a dog, okay, in image classification. Okay. But typically we will just think about one, okay, regression classification, okay, and then we can kind of wire together the loss function. Okay, so we will focus on the case that the loss function is one value. Okay, so because when we optimize, we are not just looking at y, we are looking at the loss function, and the x is actually the parameter theta. Okay, so we have y equal to fx. Okay. But this machine learning model has theta. And what we are actually doing is we define the loss function of it, or error. Okay? And we are taking derivative theta, right? Okay? This theta can be high dimension. And usually loss function will be one value. Okay? So we care about, usually here we only care about the loss function of the scale. Okay? But the input variables can be a vector. Okay? And it can be even a matrix. Okay? And it can be a tensor, right? So actually in deep learning, we care about the output is also a tensor. For example, if you have multiple layers, okay, finally you have a loss function, okay? But in between, the input output are tensors, okay? So actually they are more complicated than the simple, okay? But here we are only care about the last layer, right? So here we have the different kind of multivariable calculus ways, right? So for your y, let's say your loss function is one value, right? This is our focus value. If your y is a vector, it can also be a matrix. Right? So the x, right, the input can be just a scalar. It can be a vector, right? In our table, right? x1, x2, x3. It can also be a matrix. Right? So for example, it's a rating matrix. Right? Who rate a movie, which score. Right? So this is also called a matrix. Okay. So then, if we want to do gradient descent, right? So we want to take a derivative and set to 0, like as we see before in the first lecture, right? So then we are taking calculus, but you know it's beyond the simple one. Right? So yeah, so maybe most of you are familiar with the first one, right? Y take a derivative x, right? Now in this lecture we will go a little bit beyond. Okay, we'll go from y is a one value, that's a lot, to a bunch of theta, okay, a vector. Okay, so this is what we will do. And actually, x can also be related to theta. Right? Say if you have a linear model, right? You w1, x1, w2, x2, w3, x2, right? Take the dot product. Okay, then the weights are having the same dimension as the input dimension of the data. Any questions? If not, let's continue. Okay, so the first is the vector calculus. Okay. So in vector calculus, I think I have some. In vector calculus, right? So the G is one value, right? So you translate a vector of input, okay, into a value, okay. So the G is a function that takes n values, but the output is just one value, okay. And if we take the gradient over there, right? So what will be the result? Okay, so we define it like this. Usually when we talk about you know, vector, it's always a column vector. Okay, we will write it as a row vector transpose because we don't want to span multiple lines. Okay, this is more space efficient when we run. Okay, many lines. Okay, this only applies to one line. Okay, but actually it's a column vector. Okay, if you have your function is a scalar, right? Output is scalar, but your input is a column vector. Okay, and you take a derivative to this input vector. Okay, the result will be of the same dimension. It's still a column vector. But each element is that you take g, this function, to the first variable, will go to the first one. Okay? Take the second, go to the second. Take the last, go to the, it's a column vector, but of the same dimension as w. Okay? In general, this is the same. If you take a derivative of any to any variable, the shape is also that. Okay? That's why you can take the minus to the gradient set. Okay? So yeah, so this is just a definition, right? Vector gradient. Okay? So the definition has a deeper mathematical relations, but you just take it, okay, because this is not a math class. So this is a machine learning class. So you are using math, or you think about the applied math. Okay, right. So this is the first derivative. Okay, we also have the second derivative. Right. So if you have a second derivative, what will happen? Okay, so this is called the Haitian matrix. Right. Haitian matrix is something like this. Right. So now you take a first derivative, you g to take derivative w1. Right. Then for that you can continue to take another derivative to another variable, right? This is w1, w1, this is take a derivative w1, w2, w1, wn, okay? Here you can all the way to first take the derivative wn, right? So, and then take a derivative w1, w2, all the way to w. Okay? Any questions?
Professor, I have a question regarding Hessian matrix.
Okay.
What exactly, I mean, I'm familiar with the Hessian matrix, but I couldn't get the intuition behind the Hessian matrix. Can you give me the intuition behind the Hessian matrix, if there is any?
Oh, okay. So Hessian matrix is, is second derivative, right? So if the intuition is just consider the extreme case. If w is scalar, this w1, right? So then you only have this. This is second derivative in the scalar case. Is okay? But now
yes,
you have many dimensions, right? So you can take a derivative to this first and this first, right? So you have so many combinations. That gives you this.
Okay, I mean, what is the intuition? I mean, let's say derivative of g, but given w1 and wm, towards the rightmost corner.
Because this is n-dimensional, okay? This is more than 3-dimensional.
Yes, Professor. Yes, Professor.
Yeah, this is just mathematically, this makes sense. Also for convex optimization. These things are just, you need to think a high dimension and then you compare back to low dimensional space, okay? Right, so the only way how to understand is to think in low dimension and then see whether they generalize to high dimension. And when you want to use those generalized to high dimension case, mathematically people need to do this, okay, to be correct, and you accept it and you get familiarized with it. Okay? Yeah, so that's the only way. Okay, so you just be comfortable with it. That's the only way, right? Yeah, you want to make it intuition, then that's difficult because it's more than 2 dimensions. Okay. This is second derivative. Okay. And this is the first derivative. It's column. Okay, second derivative matrix. Okay. So you can also see that if you look at the first derivative, right? So then you take another w, right? It's the second derivative in some way. But this is actually first you take a transpose of this. Okay, right? Then it becomes a row vector. Okay, and then for each item in the row vector, right? So then you get another column. Okay.
What I was confusing is, Professor, for gradient, I am assuming it as a slope, whereas Hessian it's a double derivative. If I can even assume a double derivative with respect to single variable, but I couldn't understand what is the, let's say, in the matrix.
Yeah, I get what you want to say. So let me see whether I have an example to show. Okay. Yeah, this is a 2-dimensional case. Okay. Right. So if you think of derivative, right? So x1, x2, 2-dimensional case. This is the derivative, okay, gradient, the direction that goes the fastest. Okay, you can decompose into 2 dimensions. Is it okay? Right?
Okay.
And the second derivative is actually the curvature. Okay, so the curvature means if it's kind of this kind of shape, then it's concave. Right? So the second derivative is again. So this is a kind of like negative, but the matrix negative. It's called a negative semi-definite. Okay.
Slope of the slope
matrix is a positive, right? So it's a positive semi-definite. We will cover that later. It's okay. This is saddle point. Then it's it's kind of random. Okay. If it's a flat, then the curvature is 0. Okay. The Hessian matrix is 0. It's okay.
Okay.
yeah, but it's difficult to imagine. So yeah, you just follow these rules, and then you know. So yeah, but these are the intuitions that you can get at most at 2-dimensional space. Okay.
Yeah. Right.
Yeah, it's the same, right? So if you have 2 second derivatives, this is positive, right? And this curve is something like this. Right? The concave, then it's negative, right? If it's a straight line, the second derivative, okay? Right? Even in 1-dimensional case, it's already difficult to imagine. Go to the second. Okay? Any questions?
All right, Professor.
Yeah, and the reason that people define this in this way, because when you define this way, and then you generalize to high-dimensional, m-dimensional case, you can prove that they are similar to the low-dimensional properties. Okay, so these are what you have to take, you have to memorize. Okay, there's not much to, just like the Y matrix A times transpose, like AB transpose is equal to B transpose A transpose, right? This is just a proof. Okay, there's not much interesting stuff here. Okay, and just to be familiarized with. Okay. All right. So an interesting thing here is that if you define things like that, the differentiation rules are still holding. Okay. Let's say you have f and g, take a derivative w. It's equal to first take a f derivative w and keep g, and then also keep f and take a derivative g. Okay. So this in 1-dimensional case it holds. In the vector, the high-dimensional vector case, it's still holds. Okay. Another is chain rule. Okay, right. So if you treat this is a composite function. Right? You treat this one. Right? So you can first take a derivative from f to y, and then y to w. Okay, the chain rule we talked about that. Okay, you see both are still holding. Right. So of course they are strictly proved mathematically. Okay. All right, so these are important formulas. I see a lot of students, 3 or 4 students have that offline. Maybe it's a little bit crazy for them. But here is where we go through examples to help you understand. So you need to understand it. And so these two, the linear and the quadratic vector form calculus, we will test you in assignment. Okay, these are very important. And if you know these, you are able to read textbooks. Okay, otherwise you don't even understand what people are talking about. Right? So when you read some machine learning task. Beyond that, it depends on how many experience you have play with those high-dimensional. Okay? And TensorFlow hides all these details for you. Okay? And deep learning software. You don't need to take derivative, and they already built these models. Okay? And so, yeah, let's consider a simple function. Right? So this is a dot product between AI vector. A is a vector, okay, and WR, which is the input. Okay, right. A is a vector of parameters, right? So this is a dot product form. A1 times W1 plus A2 times W2, etc. Okay. Right. Now, what will be the derivative if we take a derivative G, which is one value, right? So this is a summation. This is one value. Take a partial derivative W vector. Okay, what will be the result? The result will be, okay, right? So because, this is A1, W1 plus A2. Okay? Just follow the definition, right? So, if this term is partial G to partial W1, okay? And, if you take a partial derivative W1, only this term has W1, right? So coefficient A1, so that's why this is, okay? If you take a partial derivative Wn, M, right? So only one term contains this, which is AMWN. Take partial derivative WM is AM. Okay? So this is just follow the definition we talked about earlier on this page. Okay? Then you will get it. So is there anything special here? Yeah, so you can write it like this. Okay, this is we require all of you to memorize. Okay? Just like how you memorize the other derivative. Okay? So if you take a dot product A and W, take a partial derivative W, right? So it will be A, okay? Because as we said, A is a column vector. We always treat a vector as column, which is this column, right? If you take a G, which is this kind of shape, to positive W, you will get A. Okay? Any questions? So how to memorize this, right? So you know, if you have AX, right, Y equal to AX, take a partial to Y to X, you will get A, right? So this is quite intuitive, right? If you scale, right? This is the same, right? So this is like Y equal to AX, right? But both are vectors, okay? And so when vectors, this have the transpose, right? So this will be transpose will be done, okay? So there are something general. You can generalize a little bit, right? So if WTA, right, take partial derivative, right? It's the same, still A, right? Because you know in the product WTA, ATW is the same. Okay, so there are different variants of this. As long as you remember this, then you remember you can derive all the others. Okay, and if you think about a extreme case, this is Y equal to AX, right? So this is extreme case. Both are scalar. Take a derivative really A, right? Because A transpose it's a scalar. Transpose is still the same. So this is a generalization of this simple form. Okay? Any questions? Okay, if not, let's go to the next page. Right, so now let's consider another function, okay? The other function is, this is called a quadratic form, okay? Quadratic function, right? So what we have is, you know, W transpose A W, that's the input W, okay? I believe a lot of people feel crazy already because I see another student left, okay? So think about it. You think about this simple function, Y equal to AX squared, okay? Right, I'm trying to help you understand. So this is a function like this, okay? Right. So you can write it like something like this, right? X, A, X, okay? Right. And because X is scalar, right? So you can take transpose, the same, okay? If you want to generalize this simple thing to high dimensional, okay? You have to do something like this, right? So this X now becomes a vector, okay? Right. So something generalized to here. Right. So this really maps this thing. Keep in mind, this shape is called a quadratic form. It's always mapped to one scalar value. Finally, okay. One. You just think about it. This is what? This is a no. W is a column vector. After transpose is row vector. Okay. And take a matrix, right? What will be the result? It's still a row. Okay. You see about the first times the first column is this value. Okay. The first times the second column is this value. Okay. It's still a row. Okay. Then times this column after W again. This is like inner product. Right? So this is one value. Okay. I hope you can comprehend this a little bit. Just to help you understand. Okay. Yeah.
Professor, can you give us the notation of W transpose A W? I mean notation. I mean in the n cross m in that manner, such that it gives me. I mean, I wanted to get some more understanding in that way.
Oh, okay. So if you want to understand in that way, so here's actually this, right? So this is how we usually do. When you see this shape, you know it's quadratic, and you know it's this one. Okay, we need to use this map. Okay.
I understood that the output is, I mean, singular value, that is scalar, but I wanted to get the W transpose. It's a row vector. I mean, it's a column.
Yeah. You want to first show this is a one row and get this form, and then times this and show that finally it's this form, right? But this is not a mathematical course. Okay, we will skip this because otherwise we will take the next 15 minutes just to do that. It's okay?
Okay, Professor.
Yeah, this is a quadratic form, right? So if you learn the linear algebra, quadratic form is a mathematical form. Okay, if you forget, if you go back to your linear algebra. Okay, otherwise, you know, for those students who already know this, it's a little bit unfair. Okay, so for Okay, so I think, yeah, this is projective form. Okay, you have a Wikipedia page telling this. If you don't remember, all you need to do is keep in mind that if you see this shape, it's this thing. Okay, right. All I do is help you memorize it. Okay? I will not derive it because it will take some time. Okay, it's beyond the scope of this course. Okay, yeah. If you want to make yourself more comfortable with it, beyond the memorize it, you can do it, expand it, write a form, and then do this and see, oh, it's really this. But we will skip this step. Okay? Even if you do this step, if you don't memorize it, it's useless. Okay. All right. So let's see what it means. So this is W1. Oh, let me see. Maybe we should spend some time here. W1, W2, Wn, let's say, okay? And this is a row vector, and you also have a column vector. Let's see how we can plot a column vector here. I'm not really sure. So maybe it's still more convenient if I'm not that familiar with latex. Let me see how to plot this, give you some intuition, okay? So this is W1, W2, Wn, okay? And this is this row vector, okay? So this is this row vector, which is transpose of column. And we also have something like here, okay? W1, W2, Wn, okay? In between, you have a matrix, okay? Which is n by n, right? So you have something like this. So like in the left corner is A11, A12, A1n, okay, something like this, right? So, and finally you have something like this is last row is A(n)(1) all the way to an, okay? Something like this, right? So if you see something like this, which is essentially this shape, okay, you need to immediately know what's the result, right? So if you think about inner product, right? So take inner product, it's something like this. But when you have a matrix, it becomes like a two-for loop, okay? Right? If you think about it. Right? So if you pick I equal to 1, j equal to 1, the corresponding coefficient A1, okay? So you get this, okay? And if you take I equal to 1, j equal to 2, right? So you have A12 times W1 times 2, okay? And basically do this all of them and then take the sum, okay? This will be the result. This helps you memorize, okay? But if you are not convinced that this thing finally is this thing, you have to prove it yourself. It's okay?
Okay, Professor. Thank you.
You're welcome. Yeah, now let's consider what's a derivative, right? So keep in mind when we take a derivative, the first is g to w1, okay? Right, g to w1, okay? Right, then all the way to g to w. Let's just take a look at one term, okay? If we take a look at g to w1 in these two levels of sum, right? If we think about this term, at least it should have one w1 in order to not be eliminated. So if you sum something term that is not relevant to w1, then take a derivative to 0. Okay, let's think about first. Let's think about I equal to 1. Okay, I equal to 1, which is exactly this case, right? So you can compare this, right? So w1, take a derivative to w1 is gone. Okay, so the coefficient is a1j wj, which is this. Okay, and you know that for I equal to 1, j has n terms, right? So that's where you get this term. Okay, next, consider you fix j equal to 1. Okay, and you know you take the derivative to w1, right? So this term is gone. This is coefficient. Okay, so this is basically this term. Okay, and similarly there are I of there are so many I terms. Okay, right? So that's why you take the derivative to w1, you have these two terms. It's okay?
Yeah, last one. Okay.
Yeah, so this for W2, W3, all the way it's the same. Okay, so something like this. Now you can write it like this, right? So so this is a G, okay? This is W, okay? Right, so now you can see what is AW, right? This is the linear equation, okay? So again, so if you are not convinced about the linear equation matrix form, then you have to be comfortable with it. Okay, so this is out of our, I think we need to use a matrix notation. Okay. Right, so let's look at this. Okay, so you can treat a, let me see. Yeah, this example. Okay, so if you have a matrix A which is 2, 9, 3, 4, and you have a non-variable x1, x2, right? So something like this. You can, it's equivalent to this linear equation. Okay, so let me see whether there's a more general form. We have to end very quickly. So yeah, so yeah, so this is the example, right? So you have these three, the A11, A12, you put it here, and X, Y, Z, you list as a column vector, and this B bias is here. This is linear equation. Okay, so yeah, it's the same, right? So if you have A, which are these X4, 2, this is the A, okay, and W is a column vector. Okay, so no value. It's here, right? Okay, and you take the result will be this value. Okay, will be this value. You see that this 8 is essentially 4 times X, 2 times Y, 6 times Z. Okay, so you see these are the terms active. Okay. On the other hand, if you look at the second term, right? This is this is 1J. This is I1. Right? It's like a swapped X and Y. Right? So this is actually equal to transpose of T. Okay. It's like you kind of make this matrix transpose, rotate to the other direction. Okay. But again, so just review these slides and get yourself comfortable with that. Right? So I assume linear equation is fine. Right? So you know that these things are equal to this column. Okay. Okay. And so this gives you this result. Okay. So if you have quadratic form, it will be equal to AW plus A transpose times W. Okay. Let's look at the extreme case. Right. So Y equal to AX squared. Okay. What will be the result after taking derivative? Who knows?
2x.
2AX. Okay.
Yeah.
Let's do the coefficient. It's okay. Yeah. If you put it, because it's squared is 2x. Right? So this is A plus A times X. Okay. And because A is scalar here, right? So you can easily add a transpose here, which gives you the evaluation. Okay. So this is to help you guys understand, right?
Understood, Professor.
Yeah. So if your A is let's say covariance matrix or Hessian matrix, right? It's a square matrix, symmetric matrix. A equal to A transpose. Then you have 2AW. Okay. Yeah. But in general, you can only say AW plus A transpose. Okay. So that's the end of today. We will continue with this slide the next time, and then we will move to the next slide. Okay.
Okay.
If you have any question, you can ask me.
Yeah, I have a. Yeah, I resolved the issue because actually I renamed the pictures you sent.
Oh yeah. So that's the problem. In your annotation file, your file has something.
I got the renamed. I uploaded the renamed picture and it worked.
Yeah.
Should I submit the renamed picture also as a homework?
Can you replace all the new name with old names? The TV will use the old name to mark. Okay.
Yeah, because is it possible to replace that? I have already got the annotation, everything.
CSV file is a text file. Okay, it's just that you can use Excel to open. Okay. Whenever you see a comma, I think it's a tab, the next cell. Okay, you can open it as a text file and replace all the file name. It's okay.
Okay.
Yeah. It's a comma separated file. Okay. Yeah. It's comma separated. Okay.
Okay, thank you. I'll do that.
Any other questions?
You mind,
Yeah.
you mind if I share my screen?
Just one moment. Let me. So let me make you co-host. Okay, yeah, you can move forward. Hello?
You can see this image I've got over. Oh, excuse me. I've got, I think about 200 of those stuff.
Oh, okay.
And this, okay, this one is one I had over 200. You can see.
I see. So I think usually we will not request those low level, those top ones. So we usually care about you know, the close and the upper front ones. But if you make more, that's totally fine.
Okay, that's why I was asking you, just because I've already annotated them. I mean, I wouldn't lose any point for those.
No, if you highlight more objects, you will not lose any point.
Okay.
Actually, we will consider giving you more points using a formula. Okay, so if you annotate more, no worry. Okay.
All right. Thank you. Just making sure. Appreciate it.
You're welcome. Any other questions?
Yeah, I'm from the Auburn section. It looks like we don't have the
Oh yeah,
latest
so I
slides.
will send it to copy. Okay.
Sounds good. Thank you.
You're welcome. Any other questions? If not, I will just get offline. Okay, so if you have any questions, feel free to send email to me. Thank you.